In this video I talk about surface fitting. The surface that we're going to fit observations is defined in line 4. I've skipped over the preamble of the script example underscore surface fit. Let's have a look at line 4. This is the custom model we're going to fit to the observations. It depends on 3 coefficients or parameters, A, B, C, and on 2 independent variables, x and y. The functional form is the one given in line 4. Now we assign numerical values to the 3 parameters or coefficients. We collect them in the vector beta, and we define a function handle that implements this custom model. Please note the function hypot at the end of the definition. This is a numerically stable implementation of the square root of x squared plus y squared. Note that the order of the arguments is important, not the names, but the order. First, we have to list the parameters or coefficients, they are A, B, C, and then we list the independent variables, which are x and y in this case. Now we're going to plot the surface. We have seen this already many times. Let's skip directly to line 34. And we see the surface in figure 1. Let's rotate it a bit to see it from different vantage points or point of views. It has 3 very pronounced maxima in the central region around the origin. Also 3 very pronounced minima, and then a couple of smaller maxima and less pronounced minima further outside. Now we want to generate observations from which we can estimate the parameters or coefficients of the surface. We define the number of observations to be 400. Then we define a set of random points in the range of x and y. If we look in lines 15 and 16, we see the range of x between -8 and +8, and the range of y between -6 and +6. So we define a uniformly set of random points in this rectangle. We evaluate the model function at these points, and we get points in space with the coordinates x, y, z, t, stands for z true, and we can plot these with green circles in this case, and these are the points that lie exactly in the surface. Now we add noise to these points, noise in z to be exact. The standard deviation of this normal or Gaussian noise is 0.05. We add a random noise, Gaussian random noise, to the true values, and we obtain the z values of our observations. We now plot the observed points. We see the red circles, they do not lie on the surface anymore, and in the projection to the x and y axis, we see they are randomly distributed in the rectangle of x between -8 and +8 and y between -6 and +6. Now we are ready to fit the surface, this parametric surface, to the data. I will show you two ways how to do this. The first one is with a curve fitting toolbox. This is entirely object oriented. And the second one is with a statistics toolbox, which is entirely procedural. Let's start with the curve fitting toolbox, the object oriented way of fitting the surface to the data. We start by defining the options of the fit by a call to the function fitOptions with some arguments. The most important one is a starting point, which we take to be the true values of the parameters. The result of this function, the output, is an object. We call it fitOpt, and its class is curveFit.NLSQ, nonlinearly squares options. An object has data members and methods. We can see the names of the data members by the function fields. So fields of fitOpt shows the following data members. The methods of this object are shown by the function methods, and here we have 6 methods that are available for this class of objects. The next object is called model1. It's a fit type. So model1 is of the class fit type. Let's again have a look at the fields, the data members. I should say the public data members, which can be accessed directly from the outside. There are none. There are no data members that can be accessed from the script. If you want to extract a value from this object, you have to use a method. So let's have a look at the methods for this object or for this class. And here you can see that you can extract certain attributes, properties from the object by using a certain method. For instance, if you want to know the name of the coefficients or parameters, you call the function coefnames, and you see they are A, B, and C. Or if you want to access the names of the independent variables, you call the method indepNames, and they are X and Y. All this information is stored in the object, but to access this information, you have to use a method. So this fit type says the function is model fun, the independent variables are X and Y, the dependent one is Z, and the options are stored in the object fitOpt. An object can be a very complex thing. It can have fields, data members, and it has normally methods. And of course, the object knows which methods can be applied to it. So it's let's say, a very independent way of storing things. You don't have to know how these objects or variables or fields are stored. You have to know which method you have to apply to access this information. Now we can call the function fit. The first argument is now a matrix of X and Y values. So this is a matrix with 2 columns. The first column is X, the second column is Y. The second argument are the Z values, the third one is the model, and the fourth one is the object containing the fit options. Now we can call this function, and we get, as a result, an object fit1 of the class sFit or surface fit, and a structure gof1, where gof stands for goodness of fit. So let's look in more detail at the object fit1. What are the data members that can be accessed directly? There are none. This means you have to invoke a method to get access to the information stored in fit1. So there are no public data members which can be accessed directly from the script. There are only private data members which have to be accessed via a method. This is very safe because you cannot accidentally or otherwise change the content of the object. If you want to extract the estimated parameters from fit1, you have to invoke the method coFValues. Let's have a quick look at the methods that can be applied to this object. That's quite a few, and one of them is coFValues, and this extracts the fitted parameters from the object. So we execute coFValues of fit1, and you see the three estimated parameters. I recall that the true values are 0.75, 1.5, and 0.5. Then we can extract the confidence intervals, the 95% confidence intervals for these three parameters. This is a matrix 2 by 3. The first row is the lower boundary of the three confidence intervals, and the second row is the upper boundary. We've seen this already in the curve fit. Now we want to predict the function value at a certain point in the xy plane. Let's say x equals 2, y equals 0. So we define a vector x0 which has the elements 2 and 0, and then we compute the prediction of the function value at this point, which is 0.3567. We can compare this to the value of the true function, which we can get in this way: model fun of a, b, c, 2, and 0. This is 0.367, so it's slightly larger. Now let's display this predicted value, and let's also display the two types of prediction intervals, one for the function, one for the observation, and we are done with the fit with the curve fitting toolbox. Now let me show you how to do the same fit with the statistics toolbox, which uses only a procedural paradigm, not object-oriented, which means that you have a lot of functions that compute the results you want, but these functions are kind of independent. They are not linked to a certain class, so they are not methods of a certain class. They are just functions like many other functions. You'll see in a minute how we can do that. First of all, we have to redefine a model function. In the statistics toolbox, it's expected that the model function depends on a vector of coefficients or parameters and on a matrix X which contains a x and y in the first and second column respectively. So I have to rewrite the model function this way. I have to replace a by beta 1, b by beta 2, c by beta 3, and x is now the first column of the matrix X, and y is the second column of the matrix X. X is now a matrix with two columns. So this is a redefined handle model fun. Now I again can set fit options. In this case I set only the maximum number of iterations, it's 250. This is done by the function statset, a function in the statistics toolbox, and fitopt is now a simple structure. It's not an object anymore, it's just a structure. And let's see what are the field names of this structure. You can see them here. There are 20 fields with the names given in this list. If we try to find methods for fitopt, you get just all the methods that are defined for the class structure. So this is a very general class and it has methods, and you can see them listed here. Now we call the fit. The function is called nlinFit. The arguments are very similar to the one in fit. We give the matrix of x and y values. So x and y are two columns of x and y values, and the first argument is the 400 by 2 matrix of x and y values. Then we have z with the model fun with the starting point. Starting point is given here as an argument, not as an option, and then the options in the structure fitopt. Now the output is not an object but just a list of variables. So this is a vector, this is a vector, resid is a vector, J is a matrix, the conv beta hat is a matrix, and MSE is a numerical variable, a double. So the output is much less organized. It's not stored in one and the same object. It's just a list of variables, vectors, matrices. Now we don't need methods. We can directly look at the produced output. So the estimate parameters, they are of course the same as before because the results, they are totally the same. Then we have the covariance matrix of the fitted parameters, a 3 by 3 positive definite matrix. We have the confidence intervals. These we get by the function NL_ci. So nonlinear parameter fit confidence intervals. And this is not the method of an object, that's an independent function which takes as an input some of the results of nlinFit, namely beta hat, the residuals, and the Jacobian J. J is the Jacobian, the matrix of derivatives of the observations with respect to the coefficients or parameters. So it's a 400 by 3 double matrix. Of course, you have to know that this function is called NL_ci. In the object-oriented version, you just call the function methods and you get a list of all methods that can be applied to the object. In this case, you have to know or to look up the function NL_ci. This gives the confidence intervals. Of course, they are the same as before, but they are organized a bit different. It's not now a 3 by 2 matrix and not a 2 by 3 matrix. So you have to be very careful, and you must not get confused by the different presentation of these quantities. Let's compare this to the confidence intervals of fit 1. So you see the two are transposed versions of each other. There's plenty of sources for confusion here. I should say a bit about the history of these two toolboxes. Well, the statistics toolbox is much older, so to speak, than the curve fitting toolbox. And that's why in the statistics toolbox you don't have objects and methods. The curve fitting toolbox is more recent. It was written at a time where the object-oriented paradigm was already there in Matlab, and of course then it was written in an object-oriented way. So where are we? We're in line 78. Now we look at the studentized residuals, which are the residuals divided by the square root of the mean squared error. And this is a very popular way of checking the fit, because if everything is okay, these studentized residuals should have approximately a standard normal distribution. So they should have mean close to 0 and a standard deviation close to 1. So let's open a second figure, compute the studentized residuals. The residuals are just the differences between the observations and the fitted surface. Now we invoke the function histogram. It's a very powerful function. Please look it up in the documentation. This is a very simple call to histogram. We say make a histogram of the studentized residuals in the vector studres with 24 groups or bins. And this is the histogram of the studentized residuals with 24 bins. Let's label the axis. Let's put a title. So the x-axis shows groups in R, where R are the studentized residuals, and the y-axis shows the counts per bin, the absolute frequency of observation in each group or bin. Histogram is very powerful. You can give very many options. You can not only define the number of bins, you can also define the range of the bins, and so on and so on. So let's display the mean and the standard deviation of these studentized residuals. You can see in line 89 and 90 how these quantities are computed. The mean value of a vector of numbers is computed by the function mean, not very surprising. And the standard deviation is computed by the function std. And we see mu, the mean, is very close to 0, and sigma, the standard deviation, is very close to 1. So this looks all right. How do we do prediction in the procedural way in the statistics toolbox? Well, you have to know that there's a function nlpredci. It's again an independent function, and you have to give to it the model function, the point where the prediction is computed, it's 2 and 0 as before, the estimated parameters or coefficient residuals, and the covariance matrix of the estimated parameters. So this is the input, and the output is then a predicted value, zpred, and a variable pred ci, which is the half width of the 95% prediction interval for the function. There is no corresponding function for the observation prediction interval, so this gives us just the functional confidence or prediction interval. And as I said before, pred ci is the half width, so the interval extends from the predicted value minus pred ci up to predicted value plus pred ci. So let's compute these values and let's display the functional confidence interval. And it's of course the same as the one we obtained with the curve fitting toolbox. Let's check this. This was the interval stored in CI func. And you see, of course, the two are the same. So the math behind the estimation is absolutely the same. It's just the implementation that is different. On the one hand, you have object-oriented, where information pertaining to the fit is stored in one place in a single object. In the procedural implementation, the information is scattered over many different variables, vectors, and matrices. You have to remember which functions you have to use, and it's not obvious how to find these functions. In the object-oriented paradigm, you can find out very easily which methods or functions can be applied to an object of a given class.